We want to talk about the work energy theorem. Very powerful theorem because it relates energy and work. In fact, you might recall we said that energy was the ability to do work. So that's terrible, okay? Let's talk about work. We said that work equals force times distance. There was a limitation. That one only worked if the force was constant. Work was also the area underneath a force versus distance graph. Well, that one was only useful if they gave us a graph. There's a third definition of work. It's the last one I try because it's a little cumbersome, but we'll be using it a fair bit, and it's the work energy theorem. The third definition of work says this: work is equal to the change in potential energy plus the change in kinetic energy. That's how much work you've done on an object. So, example 1. A cyclist weighs 65 kilograms. Her bike weighs 7.2 kilograms. If she's pedaling over level ground, how much work does it take for her to increase her speed from rest to 5 meters per second? So my brain would read this, and Gabor, I would ask myself, what's it asking me to find? How much what? Keep reading. How much work? Don't write this next bit down. The first thing I would do is I would go, well, I'd prefer to use that. Do you see a force in newtons anywhere? Do you see a distance in meters anywhere? So we scratch that one out. It's also the area underneath a force versus distance graph. Did they give you a graph? So this is from now on, when it asks how much work, the mental checklist you'll go through, and you'll end up with, I guess I'm going to use the work energy theorem, which is that it's the change in potential plus the change in kinetic energy. Well, level ground, is there a hill in this question? Is there going to be a change in gravitational potential energy? We can say that that's 0. What's change in anything? So what's the change in kinetic? I guess that's going to be kinetic final minus kinetic initial. The amount of work she does is going to be a half mv final squared minus a half mv initial squared. Now in this case, what's v initial in part A? 0. So I guess it's just going to be 0.5. I guess the total mass is going to be 72.2, I think. Bike plus rider times 5 squared. And I end up with 902.5 joules of work. Where'd that energy come from? The food energy that she ate. So she has lost 902.5 joules of energy and transformed it into kinetic energy of the bike. What if she wants to increase her speed from 5 to 10? Well, in here she went up by 5. In part B she's going up by 5. Won't it be the same answer? No, why not? This is where that squared that you don't realize is there dominates your life. So again, my brain, don't write this down. I would start out by going, work is force times distance. I would say, I don't see a force or a distance. It's also the area under a graph. Well, Captain Obvious, I don't see a graph. I would say work equals the change in potential plus the change in kinetic. Again, level ground, I would cross that out. I would say to myself, what's change in anything, Darman? And so this is going to be a half mv final squared minus a half mv initial squared. And this time, none of these are 0. Oh, if 10 is twice as fast as 5, it's going to be 4 times bigger, isn't it? Or is it? Let's find out. 0.5 times 72.2 times 10 squared minus 0.5 times 72.2 times 5 squared. What do you get? $2,727.5. Could you do me a favor, Mud? Could you go that answer divided by your answer from A? Is it 4 times bigger? Oh, you know why? It would be 4 times bigger if we went from 0 to 10. But we already used one of them up from 0 to 5. So 3 times bigger plus 1 times bigger is 4 times bigger if I combine them. So that squared thing is still holding. It's just we didn't start at the beginning. We started after we were going 5. What if I want to go from 10 to 15? Well, let's see. I'm not going to rewrite everything. I think I can just go again. 1/2 times 72.2 times 10 squared minus 1/2 times 72.2 times 5. No. 15 and 10, Mr. Dewick. 15 squared, 10 squared. Read the question properly, Mr. Dewick. Probably you can cleverly just backspace and edit on your calculator. Four, 5, 12? 4, 5, 12.5. Can you do me a favor? Could you divide that by your answer from A? I think it's going to be 5 times. Yeah? But, why is that? Well, first of all, if we had started at 0, 3 times faster would be 9 times the energy, but we've already used up 4 times the energy, leaving 5 times the energy to go from 10 to 15. But what you do notice is the faster you go, the more energy it takes for the same increase. This is why you can't just hold your gas pedal down in your car and go faster and faster and faster and faster and faster and faster. You get a diminishing return, and eventually you hit a maximum, and you damage your engine. Example 2, a 0.15 kilogram model rocket reaches a height of 340 meters when launched. If the top speed of the rocket is 85 meters per second, how much work does the rocket engine do on the rocket? Well, let's find out. Amrit, what does this want me to find? So my first thought, don't write this down, would be force times distance. Now, I see a distance, and there's kind of, I guess I could say lifting. I could probably say mg, but is there also a speed? You know what? There's some kinetic energy. I'm not going to use this. It's also the area under a graph. Did they give me a graph? No. You know what? I'm going to use the change in potential plus the change in kinetic. What's change in anything? So this is going to end up being potential energy final minus potential energy initial. There's my change in potential. And then there's a plus sign, and then kinetic energy final minus kinetic energy initial. Are any of these 0? Let's look at the potential energies. Are we ever on the ground when we launch a rocket? Initial or final? Yeah. Are we ever at rest when we launch a rocket? Initial or final? Initial. So initial is before we hit launch. Final is after the engine has burned itself out during the launching process. Okay. I guess it's going to be mgh final minus a half mv final. Don't forget the squared. No, plus, Mr. Dewick, plus. Read your signs carefully. This time it's a plus. M 0.15, G 9.8, H 85, plus 0.5, M 0.15, V 85. Don't forget the squared. I did the 85 and I'm just really in a slump right now, Dewick, learning to read my own typing. That's how much chemical energy has to be stored in the propellant. I got any typos? I think that looks good. Y'all get 1,040? 1.67? I'll call it 1,040 joules. Example 3. A car is traveling at 35 meters per second over level ground. You know what? If we're over level ground, I'm pretty sure that the change in potential energy is going to be 0. Danica, what's A asking me to find? Oh, clearly that's force times distance. Do you see a force in this question in newtons? Do you see a distance in meters? Maybe I could figure it out, but let's hold off on that. It's also the area, Danica, underneath the force versus distance graph. Did they give me? Now I would try the work energy theorem. Change in potential plus change in kinetic. But in this case, I probably could have even skipped writing the change in potential because level ground. What's change in anything? So this is going to end up being a half m v final squared minus a half m v initial squared. Oh, Danica, according to part A, what's my final speed? That's my final speed? Huh. I'm going to get negative work. You know why? Because the car needs to lose energy. That negative is telling me you got to get rid of some energy somehow. The work is going to be negative 0.5, 12, 50, 35. Don't forget the squared. And I get 765,625 joules. I'll carry the extra sig figs because I think I'm going to use it for part B. Oh, negative, Mr. Dewick. Good point. Negative. Paige, what does B want me to find? And there's a question right before that as well, after the comma. What did I find in part A? There wouldn't be a version of work that has a force in it, is there? Oh, let's try that first. I might say to myself, well, I know that work is force times distance, so force is going to be the work divided by the distance. Paige, do I know how much work was done? Do I know the distance? Oh, this is plug and chug now. Negative 675,625. I'm going to use my answer button. Divided by 82. Now, I'm going to get a negative answer. What the negative answer here is telling me is the direction the force has to be. If I'm moving forwards, which way does the braking or stopping force have to be pointing if I'm moving forwards? If at this point you kind of just tossed the negative and said, hey, Captain Obvious, I get what's going on here, I'd be okay with it. But let's keep it going. So I have times -1, because it was negative, divided by 82, and I get negative 9,340 newtons. Hey, Braden, what's C want me to find? Oh, sorry, we're not quite done. B, you're right, Paige. What was the second question it asked? What force is what's creating? What is creating the force? Where? Yeah, and the brakes on the tires, and then transmitting that to the road. Yeah. So friction is creating this force. That's why you can't stop on ice, even if you got tires. Braden, what's C want me to find? Hey, what's mu? I don't know. What's mu with you? I think I better do a free body diagram. Braden, over here is the car. What are the forces acting on it? Get the obvious one. I agree. I agree. Let's pretend the car is moving to the right. What else? Which way? Yep. What else? Don't I have to have something pointing to the right if the car is moving forwards? Ah, okay. So I think here's what we have. Let's see. I'm pretty sure this force is the force of friction, because that's the work that's what's slowing us down. So I think I can say this. Friction equals mu times the normal force, but Braden, I don't know the normal force. If I get the mu by itself, I think it's going to be friction divided by mg. Now, mu is a scalar. It's going to be positive, so if I had a negative still kicking around on my calculator, I would just ignore it. What I'm going to do is go answer button, divided by bracket. What was m? 1250? Times g. You need a coefficient of friction of, I'm going to ignore the negative, 0.762. Units for coefficient of friction. Oh, okay. I don't know if you remember, but way back in Physics 11, in the first kinematics unit, we did a question where we had somebody involved in a car accident, but there were no witnesses. But the cell phone had picked up the sound of the skid, and so that gave us a time value. And I said to you in Physics 11, we'll revisit this once we have enough physics to handle it. Well, here it is. You don't need the sound of the cell phone. All you need are the lengths of the skids, and then at the road, you measure the coefficient of friction between tires and the road. There's a little device they use to do that. So, RCMP officer is investigating an accident. Car has struck a pedestrian at a school crosswalk. No witnesses. The officer measures the coefficient of friction at the accident site to be 0.65. And he measures skid marks that are 49 meters long. Should the RCMP press charges against the driver? What's this question asking me to find? Sorry? A verdict? How? Which V? What's VF of every car accident ever in history? Yeah, it's asked me to find VI. Okay? How would I handle this? I'm going to get clever. It's going to be a little bit weird. I'm going to write maybe the most obvious statement ever. Ready, Xavier? Here it goes. Work equals work. argue with me on that. But I'm going to now write two different ways. Force times distance equals change in potential plus change in kinetic. We're going to assume we're on level ground. In real life, if you're on a hill, you can actually take that elevation change into account as well and get it in here. What's change in anything? What's my final kinetic energy going to be? In fact, this is going to end up just being negative a half mv initial squared. And you said, I want to find VI. Well, there it is. What about on the left-hand side? Well, they did give me D. That's the skid marks. Friction is what times what? Sorry, first of all, I should have, I guess, said which force is bringing us to a stop. It is friction. It's going to be mu times the, I don't know the normal force. Oh, but look. Another force same size as the normal force. What? Okay. If there was a hill, you could get the angle of the hill, and it wouldn't be mg. It would be mg two lines. It would be mg sine. We can do that too if we were on a hill. Sorry? It's this same free body diagram, right? Right. Oh! This is kind of nice. What do you notice? Well, it's convenient. In other words, if the driver tried to say, well, I had a full load, and that made it tougher for me to stop. No excuses. Now, got a bit of a problem here. This side is negative, this side is... Wait. Isn't this force in the opposite direction of this distance? Technically, this force is negative, because we would have made it negative because it's lost energy. So we have a negative and a negative. They are going to cancel out. We are going to get a positive answer. I'm positive. In fact, we can get the V by itself now. The negatives will vanish. I would times the 2 over. I'm going to get VI equals 2 mu G. Actually, that's VI squared. So, yep. This is how you could do it just from the skid marks and gathering some data at the scene. 2 times 0.65 times 9.8. Oh, I'm sorry. It should be there too, shouldn't it? Thank you. Times 9.8. I'm in a slump for some reason. Times 49. I need some caffeine. Two times 0.65 times 9.8 times 49. Two mu G D square root. And I get 24, 25 meters per second. Sure, times that by 3.6. Oh, get 90. Did this question say where it was? School crosswalk. So yeah, you got them. Right? Certainly if it's during school hours. And even if it's not, there's not too many school crosswalks that are in a 90 zone in the evenings. That's an old expression from my youth from the TV show Hawaii Five-0. Book 'em, Dano. That meant throw them in jail. You can certainly, that was way over your heads. Fine. Okay. You could charge the driver. Yeah, totally good. So you can see the work energy theorem page, very powerful, because it links work and energy, but because it also has forces inside, I can bring a free body diagram if necessary, bring in some forces. It really pulls a bunch of disparate, separate sections, although nothing is separate in physics, everything's related, but it puts it into a nice little tidy package. Going to show you a motorcycle video. This is someone who's very, very, very dumb. I stole this from YouTube. I believe this person because they posted it themselves. They were arrested shortly thereafter, okay? Dumb and Dumber. We're going to assume the mass of the motorcycle and rider is 300 kilograms. I'm making a best guess. I looked up a bunch of street bikes that are high performance, took an average mass, and then said, okay, let's add a rider onto it. So here is the video. Oh, man. Oh, it's Physics 11, Mr. Duke. The reason I picked this one, it's got the speedometer in the dashboard cam, okay? How fast are we going? Units. What? That's miles per hour? It's blurry, but if you look, yeah, those are smaller numbers. Sorry, like this is triple digits. This is kilometers already. This is miles per hour. This is an American-made street bike. Okay? So our top speed is going to be 220 miles per hour. Let's add that to our data. So part A wants us to find out how much energy is lost as the motorcycle slows. We're definitely going to have VI equals 220 miles per hour. I don't do physics with miles per hour. Convert 220 miles per hour to meters per second. 98.35 says my phone. Okay. Watch that again. If you have a stopwatch on your smartphone, can you get it out, please? We're going to time the slowdown. I was watching the V final was 100 miles per hour. We'll add that in a second. In case you're wondering, it's Vancouver Island somewhere. So get your stopwatches ready. I'll tell you when we're going to start. I'll drop my hand. Ready? And start. Stop. How much time? 16? 17? Let's use 16. We're doing some rough numbers here, and 16 is a nice number. Okay. So, VF was 100 miles per hour. Let's do the Siri trick again. Convert 100 miles per hour to meters per second. 44.7 meters per second. And T was 16 seconds. How much energy is lost as the motorcycle slows? I guess we're going to go, we're going to go with how much work was done in slowing down the energy, slowing down the motorcycle. That's going to be an energy loss. That road, did it look pretty level? Was there any change in potential energy? So work is going to be change in potential plus change in kinetic. But Owen, I'm going to argue from what I saw, no change in potential, right? No potential whatsoever, much like your future. Never mind. Okay. So it's going to be a half m v final squared minus a half m v initial squared. We're going to get a negative answer. Yeah, the motorcycle had to lose energy. 0.5 times 300 times 44.7 squared minus 0.5 times 300 times 98.35 squared. Point 5 times 300 times 44.7 squared minus 0.5 times 300 times 98.35. Don't forget the squared. I got a typo somewhere there, because there's no way I should get a positive answer. 0.5 times 300, that's better. And I get negative 1151194.875. Okay? Negative 1151194. Heck, 1195 joules. Where'd that energy go? Lots of heat. C. How many watts of power were generated in stopping? How do I find power, Mason, my friend? How do I find power? Oh, and I found work, and I got time. Oh, easy peasy. Power is going to be work over time. I'm going to ignore the negative. So it's going to be 1151195. I'm going to use my answer button. Divided by 16. So I'm going to multiply by negative 1 to get rid of the negative. And then I'm going to divide by 16. And I get basically 71,900 watts of power. So how many 60-watt light bulbs could you light up here? Well, answer button divided by 60. That's for 1 second. What if I wanted to light these for, I don't know, 60 seconds? 20 bulbs. There's a fair bit of energy here. Okay? A lot of energy here. So what do we get? How many? 1,200, right? And I think I asked this the other day. Anybody here have an electric or hybrid vehicle that has regenerative braking? So what regenerative braking does, instead of losing all that energy to heat, you only lose a tiny fraction to heat. Most of the energy goes back into recharging the batteries. And you can see there's a fair bit of power, a fair bit of energy there. Totally. Last one, I think. Yes, yes. A rocket car is initially at rest. I would probably underline the phrase at rest. on a frictionless horizontal. So if there's a change in potential energy, it's going to be 0, bonus. The engine is ignited and the graph below shows the thrust force versus distance for the car. Okay, A asks, looking at the graph, why do you think the force decreases after 15 minutes? Why do you think the force does that? After 15, not minutes, 15 meters. What do you think? Yeah. I think also it's a rocket car. You know what I think is happening? Engine's burning out. Yeah. Because this is a 5.2 kilogram car. This is clearly not a real car. This is a toy model. Engine's burning out. Okay, a little more interesting. Taryn, what's B want me to find? Wow. Speed or velocity? Maybe that's a hint to try a scalar approach. Because I don't see an acceleration. I don't see a time. You know what I do see? A graph. What kind of a graph? A force versus distance graph. Maybe I can solve this in terms of work. I'm going to, again, write down the Captain Obvious statement. Work equals work. Well, duh. The area equals the change in potential plus the change in kinetic. Oh, and Taryn, what did we say the change in potential energy was? Because it's a horizontal surface. Oh, and what was our initial kinetic energy? So change in anything final minus initial. I think we just end up with final. That tidied up that side nicely. On the left, I think I just need to get the area. Well, the first shape is a rectangle. How do I find the area of a rectangle? So length times width, or base times height, that's going to be 15 times 160. Oh, wait a minute. After how many meters, Taryn? We're done. Let's get the V by itself. Times by 2, divide by M, square root. 2 times 15 times 160 divided by, what was it, 5.2? Was that the mess? Square root. Think about, we've been able to do that. We don't know time, we don't know acceleration, we don't know none of that, but we do know how much the energy was transferred. We can figure out the final speed. And I get 30.4. C says do the same thing, but for 25 meters. I'm going to argue it is the same thing in that I'm going to start out saying, hey, work equals work. I'm going to then say the area equals the work energy theorem, change in potential plus change in kinetic. Our change in potential, still 0. Paige, I'm going to argue that on the right-hand side, you're still going to end up with a half mv final squared. But on the left, we're going to have the rectangle plus the triangle. Base times height divided by 2, I seem to recall. Yes? So 10 times 160 divided by 2. I would probably turn the left side into a single number. 15 times 160 plus 10 times 160 divided by 2. 3,200. So V final is going to be 2 times 3,200 divided by 5.2. Don't forget the square root. And I get not much faster. Well, yeah, the rocket's dying out. The force is decreasing, so you don't get much oomph, but a little more, 35.1 liters per second. That's the work energy theorem. What's your homework? Number 1 is good. 2 is good. 3 is good. I'll skip 4. 5 is good. 6 is good. I'll skip 8. 9 is good. And 10. And we're done the work energy unit. So today is Wednesday. Tomorrow we'll be marking a take-home quiz. We'll be doing a little lab tomorrow. I'll give you a study guide as well. And I think we said your test is going to be when? Monday. Is that all right? Okay. Tuesday would be cooler? Oh, just because it's a Monday? That's the last block of the, or it's after lunch. That's not too bad.